So first, I wanted to thank Alexandra and John for the invitation, and I thank everyone for coming. So today I'm going to talk about the small denominators and also large numerators of quasiperiodic Schrödinger operators. You may hear small denominators a lot from other experts in the area. So the new ingredient in this talk is the large numerators. So let's start with our model. So we are going to study the one-dimensional quasiperiodic Schrödinger operator. So the operator has several parameters lambda, alpha, and theta. So the operator is given by the free Laplacian, which is un plus 1, un minus 1. And then we have the potential, which is driven by our function. So we call the potential, the function V is periodic. In this talk, V is analytic. And the lambda is called a coupling constant, and alpha is irrational, is called frequency, and theta is the phase. So we are interested in the family of this the quasiperiodic Schrödinger operator. So when alpha is periodic, the operator becomes periodic Schrödinger operator. Then, but in this case, alpha is irrational. We call quasiperiodic Schrödinger operator. And if you write down this matrix in a matrix, the off-diagonal entries, infinitely dimensional matrix, are 1, which is from here and here, and the diagonal entries, which is given by the this guy. So we have many questions arising from the quasiperiodic Schrödinger operator. For example, you can study the spectral. Most important work of Avila and Zhytomyskaya is to prove that for almost the Matthew operator, which means that the potential V is given by the cosine, the spectrum is a Cantor set. We also care about the spectrum types, namely absolutely continuous spectrum, pure point spectrum, or singular continuous spectrum. We can also study the dynamics of the Schrödinger equation. We can study the spectrum gaps. There are many questions here. So in this talk, we focus on the spectral types. So let me give you two extreme cases. First, lambda equals 0. So when lambda equals 0, you can say that there is no potential, right? Lambda equals 0, we get a free Laplacian. In this case, it's very easy to calculate that the spectrum is negative 2 and 2, and it's purely absolutely continuous spectrum. No singular continuous spectrum, no pure point spectrum. So when lambda equals infinity, which means that after rescaling, you can think there is no Laplacian because lambda is infinity, then you get a diagonal matrix. For diagonal matrix, it has only pure point spectrum, 2 cases. So a general picture for one-dimensional quasiperiodic Schrödinger operator is that for small alpha, we expect we still have absolutely continuous spectrum. For large lambda, you can think it's a perturbation from infinity, so pure point spectrum. So for the intermediate lambda, we expect a singular continuous spectrum or mixed types of spectrum. So this is the general picture. So after decades of work by many experts in the area, so the first spectrum transition line, which I will talk it in minutes, so was well understood. So before we get into the first spectrum transition line, let me introduce several terminologies or concepts. First, we have this k-step transfer matrix. So first step transfer matrix is given by the multiplications among k matrix. So the first matrix is AE theta, which is given by this 2 by 2 matrix. And then you have the dynamics shift theta to theta plus alpha, and then theta to theta plus 2 alpha. Then until k minus 1 alpha, you do the product, you get this k-step transfer matrix. Why do we introduce this k-step transfer matrix? Because if you solve this eigenequation, here actually we have lambda v alpha theta, but I drop the dependence for simplicity. Then you get this formula. This is the eigenequation. You get here, you have k plus m. Here is m. Then you have from m to k plus m. It's given by this matrix k-step transform matrix multiplies the eigenfunction. This is a 2x2 matrix, and with the initial theta plus m alpha. So you have this obvious relation. This is why this is called the transform matrix k-step transform matrix, transfer from m to k plus m with the initial data m alpha. Then we can define the Lyapunov exponent for the quasiperiodic Schrödinger operator. So the Lyapunov exponent, which depends on the energy E, so is the average of the decaying growth rate, exponential growth rate of the transform matrix. You get the log function and then do the average. So I wanted to talk about the global theorem So the global theorem says that the Lyapunov exponent is very important to characterize the spectral types of the quasiperiodic Schrödinger operator. So we need to introduce a dynamic system. So dynamic system is that we theta from theta plus alpha. The theta to theta plus alpha, and then this is my map. I also have W to the in R2, which is a matrix multiplies the W. This is a 2x2 matrix, as I just mentioned. So this is very important. So you can understand, you say the eigenfunction, in fact, is driven by this 2x2 matrix, right? Also, you have a theta shift to theta plus theta alpha. So the reason why you can use the dynamic system approach to deal with the spectral theory of the quasiperiodic Schrödinger operators. So here we give you some results. So when the Lyapunov exponent is 0 on the spectrum, so here now we let E energy in the spectrum. Sorry, let me get E is in the energy spectrum. If E is in the spectrum, the Lyapunov exponent, which depends on energy E, is 0 for every E in the spectrum. We need more. We need, even though after you complexify the energy, you change E to E plus epsilon, and epsilon is super small. If you still have the Lyapunov exponent is 0, then it's related to the almost the reducibility of a cocycle. We call this guy is a cocycle. So this part I don't want to get too many details into it. So it's from the dynamic system. So what we're interested in is related to the purely absolutely continuous spectrum. So how can we guarantee these conditions? Actually, I can get, it's very natural. So for example, for the 1D quasiperiodic Schrödinger operator, you can show that there exists lambda naught such that when lambda is smaller than lambda naught, then this condition is satisfied. So namely, you can prove that this operator alpha theta has purely AC spectrum for any alpha theta and lambda smaller than lambda naught, which depend on V. So the spectrum type is clear. If lambda is smaller, it's a small perturbation, you still have the AC spectrum, purely AC spectrum for every parameters in this region. So if lambda is the Lyapunov exponent is positive, then it's related to the non-uniformly hyperbolicity of this dynamic system. Usually we expect it to pure point spectrum, but it's not quite clear. So this is the region we wanted to address in this talk. So for the intermediate lambda, so the Lyapunov exponent is 0, but after the complexification, so which means you change zeta to zeta plus I epsilon, no matter how small epsilon you add, you get a positive Lyapunov exponent. In this case, we call intermediate lambda. This is we call critical case. So now I'm ready to talk about the first spectrum transition of almost massive operators. So in this talk, I will focus on the almost massive operator, which when the potential V is given by 2 cosine, 1 trigonometric function, and this is the simplest analytic function. And then we use the notation lambda. So the operator now depends on lambda, alpha, and theta. For the almost massive operators, the operator is very important in physics and mathematics. I believe you heard a lot of results related to this model. So for limited time, I don't want to get into the background. So for the almost massive operator, usually we go to the Lyapunov equivalent. The Lyapunov equivalent depends on the energy E. However, the good thing for almost massive operator is that the Lyapunov exponent does not depends on the energy. It's universal. That's a log lambda, and the maximum of the log lambda and 0. So actually we can do better. So when lambda is smaller than 1, if you check the Lyapunov equivalent, here is log lambda, here is less than 0, which means that the Lyapunov equivalent is 0. Actually, you can show that even after complexification, the Lyapunov equivalent is 0. Then which means that when lambda is smaller than 1, this operator has purely absolutely continuous spectrum for every alpha and theta. So when lambda equals 1, you can say log 1 is 0. The Lyapunov equivalent is still 0. But after little complexification, you get a positive Lyapunov equivalent. So finally, people can after many work, people prove that. Oh, sorry, I didn't update my slides. This is also by hand here. So people can show that this operator has a purely singular continuous spectrum. So when lambda is bigger than 1, so this part is clear. This part is also clear. The lambda is bigger than 1. When lambda is bigger than 1, you check the Lyapunov equivalent, which is positive. So we usually call positive Lyapunov equivalent region supercritical region. In this region, by Courtney theorem or last assignment, you can show that this operator does not have any AC spectrum. No AC spectrum, which means that you only have a pure point spectrum and a singular continuous spectrum. So let me explain to you. So now lambda equals 0. Here lambda equals infinity. Lambda infinity pure point spectrum. Lambda 0 AC. So now we show that lambda here, this region smaller than 1 AC spectrum. Lambda equals 1 singular continuous spectrum. Here is pure point spectrum. So what will happen inside? So we are interested in the second spectrum transition line. Lambda equals 1 is called the first spectrum transition line. We are interested in the second spectrum transition line, which in this region, you expect there is a transition here, such that in this region is still singular continuous spectrum for lambda in this region. For lambda in this region, pure point spectrum. So right. So now I wanted to tell you. So how to guess the second transition? So can you guess where it happened? The first transition line is characterized actually by the Lyapunov equivalent, which is important from the point of view of the dynamic system. So what's the second transition? So now I will give you some hint to guess the second spectrum transition first. So now I need to introduce the phase and the frequency resonances. So let's start with lambda equals infinity. Lambda equals infinity pure point spectrum. I wanted to do the perturbation to see how far away I can go, right? What's the limitation we can do to still keep the pure point spectrum? So let's start with lambda equals infinity. Lambda equals infinity, which means do the perturbation. So lambda goes to infinity. After a rescaling, we have that this operator is a perturbation of the diagonal matrix, because when lambda equals infinity, diagonal matrix, right? And the corresponding eigenfunctions are delta functions. So which means they are well localized eigenfunctions. Now we want to do the perturbation. If you want to do perturbation, you need to consider about the separation. You need to study the eigenvalues. The diagonal entries are 2 lambda cosine. Unfortunately, this guy is dense in the range when you change k. So you know that when the eigenvalues is dense, it's very difficult to do the perturbation. So we needed to study the difference between two. We wanted to use the cutoff matrix to do approximation first and then do perturbation. Then you need to study the difference between two eigenvalues, unperturbed eigenvalues. So is 2 lambda and this guy. Then The difference is, roughly speaking, is by this guy, by the trigonometric identity. Here, the norm is given by the distance to the nearest integer. So now here is a little observation here. So if lambda is bigger, is larger, which means that the eigenvalues separated, the separation is better, then it's better for us to do the perturbation. So on the other hand, if this guy is smaller, which means that is smaller, which means that bar is worse for the perturbation. The eigenvalues, the separation is worse. It prevents us doing perturbation. So there is something going on here. So it's natural to introduce the phase resonance and then frequency resonance. So the phase frequency resonance is the guy, this guy, which is the limited soup of log function. Since this is the norm is less than 1, without the frequency resonance is bigger than 0. And also the phase resonance is from this guy, right, is bigger than 0. So we characterize the resonance by the decaying rate, decaying rate. So let me cheat you a little bit to give you some hint. So suppose here is not a limit soup, it's just a limit. Then this guy, roughly speaking, is E log lambda. You can say is the Lyapunov exponent. Right? This guy is E delta alpha theta and K1 plus K2. Roughly speaking, here is limit. And this guy is E beta alpha K1 minus K2. So as I mentioned, if lambda is bigger, Lyapunov exponent is larger, is bigger, which means that it's better for you. This one is the separation is better. It's easier to do the perturbation. However, if delta is bigger, beta is bigger, it prevents you doing the perturbation. There is a competition here to do the separation. Then it's believed that the spectrum type, as I mentioned, in this supercritical region, first, there is no AC spectrum, only singular continuous spectrum and the pure point spectrum. The spectrum types in this region depends the competition between the Lyapunov exponent and the resonances from quantified by delta and beta, right? It's very understandable. So such observation goes back to Avery Simon, Goddard Simon, and Jitomiskaya Simon. So now I'm ready to tell you the second transition line conjecture, which predicts where is the second transition line located. So Jitomiskaya conjecture that the second in the supercritical region. So let me give you something. Here is lambda. Here is lambda equals 0, lambda equals 1, lambda equals infinity, pure point spectrum, singular continuous spectrum, AC spectrum. So Jitomiskaya conjecture that the second transition line happened at the Lyapunov exponent equals the resonance, which means that delta plus beta. Right? So which means here is E equals delta plus beta. Delta and beta is given by the resonance, right? Is quantified by the resonances. So the conjecture is that in this region is still singular continuous spectrum. When lambda is smaller than this guy, then the resonance is singular continuous spectrum, which means that when the resonances beats the Lyapunov exponent, resonance is stronger. So singular continuous spectrum. In this region, pure point spectrum, which means that the Lyapunov exponent beats the resonance. So actually, we can do more. We can do Anderson localization. So Anderson localization, which means that pure point spectrum plus exponential decaying eigenfunctions. So roughly speaking, when lambda equals infinity, we know that it's a diagonal matrix. The eigenvalues, the eigenfunctions are delta functions, which are localized very, very well. So we expect in this region, we still have a pure point spectrum with good localized eigenfunctions, well localized function. Then we refer it to Anderson localization. So sometimes I just mention localization. So this is the second transition line. So it's very natural conjecture. So regarding the second transition line, there is some positive answer. There are some positive answers. we have two cases here. One case is that we refer it to as second transition in the phase, in the frequency. So when delta is 0, which means that phase resonance, is nothing, 0, then the conjecture has been proved, second transition conjecture. When the upper wave point is better than beta, localization, pure point spectrum. When the upper wave point is smaller than beta, singular continuous spectrum. So in other case, when beta is 0, we refer it to as second transition in the phase. So when the upper wave point is better, is larger than delta, localization. When the upper wave point is smaller than delta, singular continuous spectrum. So what we are going to do in this talk? We are going to study a family of phases we call completely resonant phases. We say theta, we call phase theta, is completely resonant with respect to frequency alpha if 2 theta in this counterbody set. So for simplicity, in the following talk, just think theta equals 0, because theta equals 0 is in this set. So you may wonder, why do we care about this special family of phases, right? Completely resonant phases. So I can tell you that there are so many reasons. So the completely resonant phases are very crucial in the study of the spectrum theory of quasiperiodic Schrödinger operators. One example. So by arbitrary duality. So at which I don't want to get into it. By arbitrary duality, the phase completely resonant phases corresponding to the rotation number, which depends on energy in this counterbody set. This is from the dynamic system point of view. And it's related to the spectrum gap age, these phases. So this one is important. And for this special phases, completely resonant phases, Avila and Zhytomyskaya, in their thematic problem paper, conjecture that the almost massive operator satisfies under synchronization if the Lyapunov exponent beats twice over the resonant 2 beta. So for the completely resonant phases, let's go to the definition. Now, as mentioned, you can think theta equals 0, which means that delta beta and delta, they are the same, right? Theta is 0. So in this case, we have both phase resonance and frequency resonance, and they are the same. So that's why this conjecture is a particular conjecture of the second transition conjecture, right? Which means the Lyapunov exponent beats phase and the frequency resonance, you have localization. So it's a particular case of the bigger conjecture. So what's the main results in this talk? We prove this conjecture of Avila and Zhytomyskaya, meaning the almost massive operator satisfies under synchronization if the Lyapunov exponent beats twice over the resonance, which means is the sum of the phase and the frequency resonance. And what's the new ideas behind the proof? We initiate the approach to simultaneously treat numerators. This is a very new ingredient on the denominators of the Green's functions arising from the quasiperiodic Schrödinger operators. There are 3 new terminologies here: numerators, denominators, and the Green's functions. I will explain to you in the proofs. So basically, this is the first part of the talk. So I'm going to get into the proofs, and during the proofs, I will explain these 3 terminologies to you. So before jumping into the proofs, any questions? So good. So let's get into the proofs. Good. So first, we wanted to reduce these problems to Green's functions, and definitely I will introduce Green functions in the same slide. So by Schnell theorem, it suffices to prove that any polynomial bounded eigensolution, I have an eigensolution which is polynomial bounded. So if you can show that any polynomial bounded eigensolution is in fact exponentially decay, you are done. So this is used basically in all the proofs of the Anderson localization, of all the localization proof, including random case, quasiperiodic Schrödinger case. So now we wanted to introduce the Green's function. So you say it's the natural way is that you do approximation. You cut off this matrix. Then we choose an interval x1 and x2. I cut off this matrix, right? I choose the finite box, which are x1, x2 is the restriction. I cut off this matrix. I get the inverse. The inverse is called Green's function. First, the inverse, namely the Green's function, depends on the interval you choose, the box you choose to cut off. Secondly, it depends on the parameters lambda, alpha, theta, and the energy you choose. For most of the time, I omit the dependence of alpha, lambda, theta, and energy. So just simply write it down as g, x1, and x2, since the operator is always fixed lambda, alpha, theta. So this is the Green's function. So now I'm ready to talk about.
Sorry. So this inverse here, it's the inverse as an operator seen on this finite dimensional restriction, right? So it's,
yes.
It's sort of okay.
Yeah, it's a matrix. It's a x2.
Yeah. It's the inverse of a finite block. Yeah. Okay.
Yeah, block. So this is why I will mention block expansion immediately. So good. So now I wanted to give you the first, the original strategy to prove it. It's back to last, back to 1990s. So at that time, so strategy, when I choose y, so let me explain to you this way. Now you have to choose an interval, x1, x2. I choose a point y. Here is 0. So it's very easy to say that if you have an eigen solution in energy y, you can solve phi y by the Green's function, and here is x1, x2. You have x1 minus 1, x2 plus 1. So you get this formula. This is the Green's function. x1 y is the entry of this matrix, right? This is a matrix. So x1 y is just the x1 rows, y's column, and you have, and then you multiply the eigenfunctions at the site x1 minus 1, x2 plus 1. So this is due to the fact that the original matrix is a tridiagonal matrix, and the off-diagonal entries are 1. Right? Then you can do the simple calculation to get this formula. So the good strategy to prove the localization means that I wanted to prove that phi y exponential decay. In order to prove the exponential decay of this eigenfunction, you only need to show that the Green's function are exponential decaying. So you can say Bogan has a book in 2005 which is called The Estimate of the Green's Function. Basically, this is a whole book devoted to proving the exponential decaying of the Green's function. So but usually it's not enough. So you have x1 and x2. Even though you show the Green's function is exponential decaying in the sense x1 minus 1, here is say x2 minus 1. This is the meaning of the exponential decaying of the Green's function, which means that the Green's function decays, the entries decay exponentially when they go far away from the diagonal entries, like the top-list matrix. So which is, even though this guy is exponential decay, this guy is exponential decay, and this guy is polynomial bounded. We only need to focus on the polynomial bounded eigensolution. It's not enough, because if x1 and the size of between x1 and y is small, but I need to show that exponential decays at the cy at the y side, which is not enough if the size of this guy is too small. So what should we do? We usually need to do more. So here, after the first step, here. After the first step, you show this guy is exponential decay at this rate. And then you get x1 minus 1. And you apply this formula to x1 minus 1 again. I choose another interval between this two x1 minus 1 and in this interval, and I continue to do the same procedure. Then we do expansion, we call Baroque expansion, we do expansion until you achieve 0. And on the right side, you can always do the, as many Baroque expansion as you can. But in the left, you can only do the approximation, Baroque expansion until you reach 0. Then you are done. This is the procedure. So which means this strategy to prove the localization turns out to the proof of decaying of the Green's function. So this is the first thing I wanted to mention. So now I want to introduce the small denominators. I introduce the Green's function and show the importance of the Green's function. So now I want to introduce the small denominators and the large numerators. So now let's denote this P is just the determinant of this matrix. As usual, it depends on the parameter lambda, alpha, theta, and the energy E. I also omit the dependence. So by Cramer's rule, the Green's function, I need to estimate these two guys, right? Equals the denominator are the same, just this, determinant. Then you have this numerators. The numerators, sorry, here you have x1, x2, here you have y. x1, y equals from y plus 1 to x2. Right? And then y, x2, from this guy, equals x1 minus here, from x to y minus 1. This is also due to the fact that this original matrix is a tridiagonal matrix. So our goal is to show that the Green function decays exponentially, which means that the denominator cannot be very small. If it's small, we are bad. The numerators cannot be very big. So these are small denominator and the large numerators. So now I finished all the new concepts. So now I wanted to mention how to, in order to solve this problem, you wanted to show that there is no small denominators. There is no big numerators. But the small denominators is very easy to happen, right? Because if you check this determinant, the determinant can be 0 because the determinant depends on theta. For some specific theta, definitely the denominator is 0. This inverse doesn't even exist. So you have to find some way to avoid this denominator, small denominator. So first, let me talk about the numerators. The numerators is easy to handle. So as I mentioned, I introduced the dynamic system at the beginning by the unique ergodicity and the upper semi-continuity. One can bound the numerators very well. The numerator is essentially bounded by the Lyapunov exponent plus some epsilon. This guy is the Lyapunov exponent. It's true for any quasiperiodic Schrödinger operator in 1D quasiperiodic Schrödinger operator if you just replace the log lambda by the Lyapunov with the Lyapunov exponent. So the numerator is very easy to handle. This is why people hear that in order to solve the spectral theory of quasiperiodic Schrödinger operator, it turns out that to solve the small denominators problem because the numerators are easy to deal with. So let me say more. So first we can say that the averages of these numerators, of the denominators, is big. Is also the Lyapunov exponent. So average is good. So which means in averagely speaking, the denominator is big. So if you can show this is not average, it's true for every theta, then you are done. Because if this is true for every theta, then the gross Lyapunov exponent rate, epsilon, you always ignore it. The numerators gross at most Lyapunov exponent. You can do the here, procedure I mentioned here, and then do block expansion, do everything. Finally, you can show phi y decays at the Lyapunov exponent rate. You are done. But this is average, not individual theta. Not for individual theta. This is the difficult part. So there are several approaches to deal with it. First, you may hear large deviation theory, which is also popular in the quasiperiodic operator also have the random version. So people study the random matrix. You heard of the large deviation theory, which means that after you remove a small set of theta, I have very good lower bound, because averagely speaking, we have a good lower bound. So another way is to study the trajectory of theta plus L alpha. So this is the one I will use. So let me give you some explanation about theta plus L alpha. For example, the proof is quite technical. I can only give you one case, one example. Here to explain what's the meaning of trajectory of theta plus alpha. So let me give you some explanation first. So now we have x1, we have x2, we have y. Averagely speaking, this guy is very good. I wanted to show that individually is good. So, but there is something you can do, because you can shift this interval. You only for every given y, you only need to find an interval, proper intervals x1 and x2, cover y. There is something you can do. You can play with the difference of x1 and x2. So suppose we have a polynomial p theta, p x1 x2. No, sorry, I don't want. I didn't introduce a polynomial first. So suppose you have this denominator p x1 x2. Now I shift this operator by 1 unit. If you shift the interval by 1 unit, because the original matrix has a natural dynamic system inside, it's equivalent to you shift this theta by 1 unit, shift the theta to L alpha. So if you shift it by L unit, you get p, the denominator, and shift the theta plus set L alpha. By ergodic theorem, if you shift it by a long scale, you achieve the average, right? Ergodic theorem says that if the trajectory finally average equals this, you can achieve this average. So the idea is that you shift it, you find one L such that the denominator is not small, but you cannot shift x1 in a very long scale. You can only shift x1 in this region. So which means we need a quantitative version of the ergodic theorem here, like similar arguments here. So let me tell you one example. So let us denote k just this x1 minus 1 plus 1. And you know that the determinant is the matrix, and the matrix of diagonal entries are 1. Of diagonal entries are 1. The diagonal entries is given by 1, given by cosine, 1 cosine. So definitely, finally, you get a polynomial of cosine. So actually, it's a polynomial of cosine with degree k. So it's a polynomial of degree k. We wanted to use the Lagrange interpolation theorem to show that at least one point YL, if you shift it, this polynomial cannot be very small. Sometimes I just mention polynomial, but actually it's a polynomial of this trigonometric function. So in order to use the Lagrange interpolation theory, you know that we have the YL minus YL Y prime, the denominator, right? Lagrange. Then which means you also need to study the difference between 2 points, right? There's 2. The difference between these 2 points, it's the same. It's this guy. After you change L1 to L1 prime, you see if you use Lagrange interpolation theorem to study the trajectory, is very similar to the resonances the separation of the unperturbed eigenvalues I introduced here. Actually, this is a bridge. Right? Both of them related to this guy. So after this. So now I'm ready to talk about the first strategy. The first strategy, how to show, as I mentioned, how to show the Green function is exponential decaying. As I mentioned, averagely speaking, you have this lower bound. And when beta equals 0, delta equals 0, by the Lagrange interpolation theory, you can finally show that for any theta, there is some L in this region, in this consecutive sequence, such that P have such lower bound. So this is a way in 1999 Wencai deal with this case when both beta and delta equals 0 to deal with the resonances. But actually, the actual proof is much more dedicated. Why? I can give you some explanation. Here you have x1, here x2, here y. In order to show that you have a good L, such that it has good means that you have a good lower bound. Here you can only shift L in this region. But in order to get the Lagrange, use the Lagrange interpolation theory to do it, you need to find at least x1 minus x2 plus 1 is bigger than the size and plus 1 point. But you only have you can only shift in this region, which is not enough. So in the actual proof, we usually need to find another interval, not like the consecutive interval. Choose another point to show that, we can find a good L. So, but I don't want to get into that. This here is just one example to show that we can use the Lagrange interpolation theory to study the trajectory of theta plus L alpha. So this is the way to deal, you can show that then you have the lower bound, right? Not average, it's for every theta, and you shift it, the intervals. So as I mentioned earlier, we have other results to prove the localization for the other cases. Here is some results. So Avila and Wencai prove that in their 10-material problem, or case step to prove 10-material problem, they show that if delta equals 0, and then the Laplace exponent is bigger than 19 divided by 9, then 19 divided by 9, then localization. And my collaborator and I pushed the limit to 3/2. And then finally we prove that when there is no phase resonance, the Laplace exponent beats the frequency resonance localization. When there is no frequency resonance, the Laplace exponent beats phase resonance localization. So there are many new ingredients in those proofs, but I only wanted to mention two most important ingredients. The first, we heavily use the continued Fluxing expansion of the alpha to alpha. Second, already studied the arithmetic property of this frequency alpha. Secondly, the Green's function is not necessarily exponential decay in these arguments. So why? So let me go to this original proof. So you see that before we show that the Green function, the paper in Jim Tokai's 1999 paper showed that the Green function decays every step. But the new nice observation is that even I will do the expansion many steps. Even some steps of the Green function that they don't exponentially decay, even we allow them exponential growth. But for the other steps, the Green's function decays super fast. We are still safe. So this is a new observation in the arguments. So after all the preparations, I'm ready to talk about it. I wanted to put all the pieces together and introduce the numerators to finish my proof. First case, I want to deal with the non-resonant size. The resonant size is 1 corresponding to y in the integer. So what's the non-resonant size mean? First, I only focus on this region, negative to Qn to Qn. Qn is a continued fluxing expansion to alpha. So let me give you some explanation. So now we have 0. Let's set the here Qn, here is 2Qn. So here is 1/2 Qn. Just assuming Qn is even. I don't want to, it's the other case is similar. So non-resonant sites, which means the y, the eigenfunction in this region, very far away from 0 and half Qn in these two regions, in these regions. So for example, I only take this guy into consideration. In this region, the small denominator problems, the separation of the eigenvalues, the resonance is L plus L1 alpha, as I mentioned, plus another guy is L plus L2 alpha. Then we have theta plus L1 alpha by the trigonometric identity, do you remember? And the theta plus L1 alpha minus theta plus L2 alpha. In this region, as I mentioned, you can think theta equals 0 because this is a complete resonant cases. Just think theta equals 0. Then this guy you get L1 plus L2 alpha. Here you L1 plus L2 alpha. However, when L1, L2 in this region, L1 plus L2 never in this guy Q. Because L1, L2 also in this region, they never equals the multiple of Qn. As we knew that for the continuous fluxing expansion, Qn alpha is the best approximation. So now in this case, L1 plus L2 not the multiple of Qn. It's basically there is no small denominator at all. In this case, here is a similar thing because the size is less than 1. It's less than Qn, right? L1 minus L2 can never be in Qnz. Let's say that never be multiple of Qn. So there is no small denominator at all. So in this case, actually, the proof is similar to the case of the original proof of J-Thomas-Kaya. Just think beta alpha delta equals 0. There is no resonance. So finally, this is the way to deal with this case. So now we want to deal with this is standard basically. This is not new in my proof. Just use what we have from previous approaches. So now we want to deal with resonant case. Resonant case is that half Qn and Qn. So for simplicity, I just take half Qn into consideration. So we have Qn, you have half Qn. So you may think for the second transition non-conjecture, when there is no frequency resonance, we prove it. When there is no phase resonance, we prove it. So how about you think add it together to prove the resonance for this conjecture, for this complete resonant phases? Oh, it's a very natural way to think, but there is some new difficulty for the complete resonant cases. I will explain to you. So now the natural way in this case, now I need to think about the half Qn because in this region we are done. In this region they are done. We need to think about the interval covers half Qn. So the best way to construct this interval, I don't want to get into the details, is that you construct it in this way. Here is negative quarter Qn. Here is quarter Qn. Here is 3/4 Qn minus 1. If you construct the interval in this way, we also have L1 minus L2, L1 plus L2. But now L1, L2 in this region. Since L1, this is why I construct this size, this interval is less than Qn because this is negative quarter Qn. Here is Qn is less than 1 Qn, which means is not in Qnz, right? Because the biggest size is less than Qn. But in this case, maybe equals Qn. Maybe equal Qn. You see right here, if L1 is smaller than half Qn, L2 is a little bit bigger than half Qn. If you want to cover half Qn, you will get into this small denominator, Qn alpha. Right? This is the upper exponent. Oh no, this is not. This is the continuous fluxing expansion problem. So, but for the complete resonant phases, you cannot construct the interval in this way. Why? Because now your function is cosine 2 pi theta. Cosine is an even function. Even function, which means this part and this part, they are the same, the values. So this part is useless. You cannot construct the quarter Qn here, which means you can only construct the intervals in this way. So this is the reason why you cannot simply put those two cases together to prove this problem. There is something new here, which is called completely resonant phenomenon here. which is really difficult to handle. Right now, you lose quarter Qn. You only need to do this guy. So reason why, if you just simply put those two approaches together, you can only prove 4 beta. So 3 years ago, I used I improved the Lagrange interpolation theorem version. I was able to prove 3 beta. I don't want to talk about the improved version here because we are running out of time. I only need the last 3 minutes. So for what's the new ingredients in our proof, we need to use all the approaches I just mentioned, plus the following new ingredients. So I can only explain to you what's the new ingredients here. So as I mentioned before, let's see the denominator, numerators. People only estimated the numerators by the Lyapunov exponent. Actually, in many cases, this Lyapunov exponent rate is optimal. But here we have a new observation. What's the new observation here? So now let me give you. It's almost beta alpha Qn by the continued fluxing expansion. So you say that if beta alpha is big, is larger, is large, which means that is large, which means that it's bad for you to prove the localization. Because beta alpha is big, which means that you have stronger resonance. Resonance is bad for us. But my the observation is that if beta is big, which means alpha is well approximated by a rational frequency. So now we have an operator lambda alpha theta. We have alpha Pn over Qn theta. For periodic Schrödinger operator, we knew that it has spectrum band structure. And for the energy in the spectrum inside this spectrum band, we knew that the Pn actually is bounded, is a constant bounded. And by Foucault theory. And if the energy is in the spectrum edge, it grows at the most linearly. What does it mean? Which means that for periodic Schrödinger operators, there is no big numerators at all because everything is bounded. It all linearly grows, which is good. So our observation is that if beta is super big, which means alpha is well approximated by rational number, in some sense it's good for us because we can pass from rational number to irrational number. This is something good we can use. If beta is good, is very big, it's bad for the resonance, but it's good for the numerator, right? Because we can think about it. We can think it's a periodic Schrödinger operator. So actually, such observation has already been used to prove singular continuous spectrum. We borrow this idea to show this localization. So secondly, this is not enough. If you even though you use this numerators and you estimate, you can improve a bound from 3 to probably 2.5, but it's not 2. So what's the final ingredient? The final ingredient is here. I wanted to mention here is y. Here you have x1, you have x2. As I mentioned, let's just take this guy into consideration. This is the numerator for y. But this guy is a numerator for y. If this numerator is big, it's bad for y, right? Because its numerator is big, it's bad for y. Because we wanted to show that the Green function around the y is exponentially decaying. So if this guy is big, it's bad for y. But x1, y minus 1, at the same time, is the denominator for the site inside y prime. If you choose y prime and I choose the interval here is x1 prime, x2 prime, this guy is the numerators for y, but is the denominator for y prime. So which means if it's big, it's bad for y, but it's good for y prime. There is another thing you can play here. So basically, finally, we use these numerators as variables. We solve this, we establish a lot of relationships, a lot of inequalities among phi y is the eigenfunction, as I mentioned, and the numerators. Finally, we eliminate the numerators. And good is, large is good for y, large is good for y prime, small is good for y. So those ideas inside. Then we are able to establish the relationships among phi y, which allow us to complete the proof. So I'm sorry, I cannot get into the details, but I can tell, you can feel, this is something new here we can play. So that's all I wanted to say. Thank you for your patience.
Thank you very much for the talk. Does anyone have any questions today? So I'll start with one. So you have improved recently this 16/9 bound to 3/2 delta, 3/2 beta for those resonances. Is this 3/2 seemingly optimal, or is it only technical, the reasons why you can't?
Good question. So this 3/2 actually is the optimal approach, in the optimal, technical limit in this the approach in their thematic problem. So finally, we had some new ingredients. We finally prove this can be 1.
Oh, so it can be 1, in fact.
Yeah, in fact, we finally prove it. It can be 1.
Okay.
Oh, sorry. So this is the partial result. Before we can only prove 3/2, but finally, James Kayas and I were able to prove. We are able to prove it's 1.
Okay.
But in this case, delta is 0.
But only when it's 0. So
yes,
when it's not 0, do we have any idea of how they play, of what's the interplay between delta and beta, both non-zero?
Yeah, so this is why this is still very difficult problem. I think I did some calculation. So for example, it's related to the second transition line conjecture, which means both of them are not 0. So I can say I can get a 16 or 20, something like that. It's a big number, but it's not 1.
Yeah.
If you check the proofs we have, you can get some numbers. You can always get something. Numerical numbers, if you do better, you can get better, but definitely it's far from the 1.
Yeah. Do we have any other questions for the? If not, I mean, I'll go for another one. So what, I mean, I guess this is the kind of question that you might get quite often, and I'm not sure how easy it is to see or whatever, but what makes this much more difficult to bring to a higher dimensional operator? I know there's not many results for, say, this in Z2. And what makes the transition from Z to Z2?
Yeah, I know your question. So the first, there are 2. I believe the most difficult part is we didn't have the continuous fluxing expansion.
Okay. Yeah.
For 1D, we have we really, first we can, as mentioned, we can use the you have the good approximation, and also we have for 1D, sometimes we need to use the periodic Schrödinger operator to do the approximation. For 1D, the periodic operator is very well understood. For higher dimension is also very difficult problem.
Yeah.
So there's 2 parts. One is because we need to use a continuous fluxing expansion. So and then sometimes reduce it to periodic Schrödinger operator. So it's difficult. And also even the diaphragm exponent, we didn't have the definition for the higher dimensional cases. You cannot transfer it to a dynamic system. So this is also another difficulty. So basically, most of the ingredients are not, there anymore for higher dimensions. The dynamic system here is also, we cannot write it down in this way.
Yeah, I see. Yeah, this seems like a problem that's already quite technical in 1 dimension. Are there any questions for the speaker today? Well, if not, let's thank him again. Thank you for giving this talk today, and we will reconvene next week with Jürgen Jost, who will talk about the spectra of graphs and hypergraphs. So see you all next week, and thanks for being here this week.
Thank you. Bye-bye.
You're welcome. Thanks.
Thank you for the talk.
Thank you, Alexander.
Be safe teaching, please, please, please.
Thank you.
Cheers.